Section 4.5 deals with oxidation-reduction reactions. Sometimes we refer to these as redox reactions. So oxidation is the loss of electrons and reduction is the gain of electrons. And we like to use this acronym here, OIL RIG. So OIL stands for oxidation is losing and RIG stands for reduction is gaining. So oxidation is losing electrons and reduction is gaining electrons. We're going to talk a lot about electrons in this section. So the oxidizing agent gains electrons and gets reduced, and the reducing agent loses electrons and is oxidized. So oxidizing agent and reducing agent. Remember, the oxidizing agent is what affects the oxidation and becomes reduced, and the opposite holds true for the reducing agent. So a redox reaction involves electron transfer. And oxidation and reduction, these always occur together. You can't have one without the other. So if we take a look at figure 4.16, it shows the formation of an ionic compound and the formation of a covalent compound. And with an ionic compound, we have magnesium and an oxygen, and you can see that magnesium is transferring 2 electrons. Magnesium has 2 valence electrons and is transferring these electrons over to oxygen to give us oxide, so O2 minus. So again, it's a transfer of electrons. And if you were wondering who's being oxidized and who's being reduced, well, the magnesium is being oxidized, right? Because it's losing electrons. And you remember that oxidation is losing. So magnesium is being oxidized. Conversely, reduction is gaining electrons. And if you're wondering who's being reduced, well, the oxygen is gaining electrons. Therefore, it's being reduced. With the covalent compounds, this involves more of a shift of electrons. So when a covalent compound is formed from its elements, like HCl being formed from hydrogen and chlorine, there's more of a shift of electrons rather than a full transfer, and thus ions do not form. So if we take a look at H2 plus Cl2, so that's what's being demonstrated here. We have hydrogen gas plus chlorine gas. To see the electron movement, we'll compare the electron distribution in the reactant and the product. And if you look at the H2 molecule and the Cl2 molecule, you see that the electrons are shared equally between the 2 atoms. Because the chlorine atom attracts electrons more than the hydrogen atom in the HCl molecules, okay, the electrons are shared unequally. So the electrons shift away from the hydrogen and they shift towards the chlorine because chlorine has more of the negative charge because it's more electronegative. It has a greater propensity or ability to withdraw or pull electron density towards itself. So the hydrogen atom has the less negative charge. So it's more delta plus than it had been in H2. So what's the take-home message? Is that H2 loses some of its electron charge and chlorine gains some electron charge. Let's take a look at the rules for assigning oxidation number. So it says that an atom in its elemental form has an oxidation number of 0. So this is any element on the periodic table except for things like the diatomic elements or phosphorus, which exists as P4. So they all have an oxidation number of 0. So if I just pick an element like aluminum, it would have an oxidation number of 0. For a monatomic ion, the oxidation number is equal to the ion charge. And we put the sign before the numeral. So say, for example, sodium always has a charge of +1, so we would write +1 like that. So we put the sign before the numeral. Let's say we're talking about calcium, we would say it has an oxidation number of +2 because it always loses 2 valence electrons to have a charge of +2. So that's how we would represent oxidation number. The sum of the oxidation number values for the atoms in a molecule or a formula unit of a compound equals 0. The sum of oxidation values for the atoms in a polyatomic ion equals the ion's charge. So the first part is just saying, okay, well, if I have, something like carbon dioxide, if I add up the oxidation numbers for oxygen and the carbon, it should equal 0 because carbon dioxide doesn't have a charge. Whereas if I have a polyatomic ion, let's just pick like something like sulfate. So sulfate has a 2- charge. So that means in this case, when I add up the oxidation numbers of the 4 oxygens and the sulfur, I should overall have a charge of 2- or -2. Let's take a look at the rules for specific atoms or periodic table groups. So group 1A everything has an oxidation number of +1, so +1 in all compounds. So these are, sodium, lithium, potassium, so on and so forth. For group 2A, also kind of easy. Everything has a charge of +2, so that's magnesium, calcium, strontium, barium. For hydrogen, most compounds you're going to see that hydrogen is going to have an oxidation number of +1 when it combines with nonmetals. An exception would be when hydrogen combines with a metal or boron, then it's going to have a charge, an oxidation number of -1. So for example, in sodium hydride, sodium has an oxidation number of +1, whereas hydride has the oxidation number of -1. Fluorine, again, kind of easy to remember. It's -1 in all compounds. Oxygen is almost always -2, except for when it's in a peroxide, and in those cases, it has an oxidation number of -1. And then for group 7A, so group 7A, you might think of the halogens, fluorine, chlorine, bromine, and iodine. So they have an oxidation number of -1, so -1 in combination with metals and nonmetals, except for oxygens and other halogens that are lower in the group. So let's take a look at a sample problem. So it says here, figure out what the oxidation number for each element in these species is. Okay, so let's take a look at the first one, A, so zinc chloride. So we'll write out the formula for zinc chloride. And if you remember that when chlorine is combined with a metal, it has an oxidation number of -1. And since I have 2 chlorines in zinc chloride, so -1 times 2 gives me a total of -2. That means that my oxidation number for zinc must be +2. So my zinc is +2 and my chlorine is -1. Let's take a look at another example. If I have sulfur trioxide, you remember that the oxidation number for oxygen is -2 unless it's in a peroxide, and sulfur trioxide is not a peroxide. So I have -2 and I have 3 of those oxygen atoms, so that gives me a total of -6. So if I have -6, that tells me that the oxidation number of my sulfur must be +6 to balance that out. So my sulfur is +6 and my oxygen is -2. Let's take a look at nitric acid, so HNO3. My hydrogen is going to have an oxidation number of +1 because it's combined with the polyatomic ion nitrate, which is completely made out of nonmetals. So my nitrate has a charge of -1. Oxygen always has an oxidation number of -2 unless it's in a peroxide. Nitrate isn't a peroxide. So I have -2 times 3. So -2 times 3 gives me -6, and I need to end up with an overall charge of -1. So my nitrogen must have an oxidation number of +5. So my hydrogen has an oxidation number of +1, my nitrogen is +5, and my oxygen is -2, like that. Let's take a look at the dichromate ion. So dichromate is Cr2O7, and it has a 2- charge. So again, oxygen has an oxidation number of -2. Unless it's in a peroxide, this is not a peroxide. There are 7 of them. That gives me -14. So I need to balance out -14 so that I end up with 2- charge overall. So that means I'm going to need a total of +12, because +12 plus -14 gives me 2-. So if I need a total of +12 here, and there are 2 chromium atoms, that tells me that my chromium must have an oxidation number of +6. So again, my chromium has an oxidation number of +6, and my oxygen has an oxidation number of -2.